Hello all, welcome to my course on methods of adhesion measurement, theory and practice. We are at lecture 45 today and we are discussing about an sandwich elastic adhesive. In the last few lectures, we have talked about this rectangular geometry in which this elastic adhesive film was sandwiched between these two rigid plates, rectangular rigid plates, and we applied this plane strain approximation along this y direction, and then we solve the problem for the case in which the film is at frictionless contact and also at no slip contact at the top surface. The film remains strongly bonded in both cases at the bottom surface over here. This is at z is equal to 0 and this is at z is equal to h. So, this is what we have discussed, both perfect slippage and complete and no slip boundary condition, no slip contact. Now, and also we have discussed about compressible film and incompressible films. So, today we will like to discuss about the cylindrical geometry in which it is the disc shaped film that remains sandwiched between these two parallel plates. So, this film is again incompressible elastic and it is loading of layer will be with and without adhesion, and we will consider also we can consider in presence and absence of slippage. Although I will not have time to discuss all these combinations, but I will discuss some of these combinations which will be helpful for you to deduce in other combinations or other settings as well, other conditions as well. So, here to obtain the pull off load cylindrical geometry, in the cylindrical geometry we have to first solve this stress equilibrium relations. So, the stress equilibrium relation in the cylindrical geometry will be given by this. Remember, we have here theta symmetry in the sense that r it is along the r direction is this and z is along this direction, and then the theta is theta is in these directions. So, this is theta symmetric case. So, therefore, the stress equilibrium relation you can see any elasticity book, you will see that after simplification we get these two equations, and here we have substituted in order to deduce that following relations, these relations for the stresses, stress and strain. And remember, since it is an incompressible film, we have directly written this sigma rr in terms of hydrostatic pressure inside this film. This hydrostatic pressure is equal to negative of normal stress at this surface, top surface, remember all that. So, we have done all that, and this is what is expressed over here, that the load applied is F. So, sigma z is the stress at the top surface into 2 pi into r dr and integrated from 0 to a, that gives the total load over here. And in the top surface, this W is the deformation at the surface. So, it is given as delta here. So, in addition to that, u is equal to 0 at z is equal to 0, and here u is equal to 0 at z is equal to h as well, because it is a no slip contact, let us say we are discussing. So, these are the conditions we have already done, only thing is the geometry is different. So, I will like to quickly go through this equation. So, here we can write it in dimensionless form, and we have done the same way. Remember that capital R can be the so a small a, that is the radius of this disc. So, that actually is the characteristic disc length in the r direction. So, that is what have been used here, and then h is in the z direction, this is h, and in the r direction this is a, let us say, and p star is equal to p star is as usual, this is mu by epsilon square, and epsilon square is mu by h by a whole square. So, that is what have been used. So, you do all that, this is with we have already done similar things. So, I am not going to repeat it here, and then finally, we will get for the r direction stress equilibrium relation something like this. And remember here this epsilon square and epsilon square term, these are very small. So, we have to neglect these terms. So, in essence we will have actually del p by del r is equal to del square u by del z square. Again, the other stress equilibrium relation, that is in the z direction, that can be represented like this, and here again we non-dimensionalize these equations, and finally over here this is, you remember say here that this is h by a. So, this is equal to epsilon square, and this is h 4 by h to the power 4 by a to the power 4. So, this is equal to epsilon to the power 4. So, again this is negligible, this is negligible. So, we have del p by del z is equal to 0. So, the results that we got, okay, in both this rectangular geometry and cylindrical geometry, they are basically same. Okay. So, these are the equations that we need to solve, and this also we had solved it earlier. So, this u, okay, comes out to be like this. So, we have done it already. So, I am not going to do it, I am quickly passing it over, and then here a over a as a function of capital R. So, capital R is equal to R by a, by the way. So, that we can deduce it like this, and so therefore, we will have u, let me write down the expression for u, therefore, we will have is equal to z square by 2. So, it is, let us say I write it as dp by dr, okay, into 1 by t, and this is z square minus this is z, okay, z square minus z, right. This is dp by plus no, AR is already have solved out, okay, that is fine. So, this is like that, and then we can so this is the expression that we have, and we are using this incompressibility relation. Incompressibility relation where we can use, and this is the non-dimensional form of that, and from there we can get the w by also and by integration. So, here we got w is equal to like this, and here remember that I have used here that w is equal to 0 at z is equal to 0, that I have already used here, okay, although did not mention it, but it is there. So, at z is equal to 1, w is equal to this w is equal to delta, capital delta over here, and that gives rise to this delta is equal to minus 1 by 2 r and del by del r, and here it is r, yeah, z is equal to 1. So, it is r by 3 minus this is r by 2, and this is dp by dr. So, this is yeah. So, now this is 1 by 2 by 6 minus 3 by 6 minus 1 by 6 minus. So, it will write it as 1 by 12 r del by del r, this is r, actually d by d is fine, because p is a function of only r now, dp by dr. So, we get like this. So, this equation now we can solve with respect to p. So, let us do that. So, here it will be, let us say d by dr into r dp by dr. So, that will be equal to, this is 12 delta and into r. So, integrating it, it will be r dp by dr is equal to 12 delta into r square by 2 plus some constant. So, let us see the constant, I have to write some constant. So, the constant here is, let us say a dash, okay. So, here, yeah, so constant is a dash, this okay, that is fine. So, this is equal to 6 delta r square plus a dash, and now this is equal to dp by dr. So, that is equal to this is 6 delta into r plus a dash by r. So, now integrate it once again. So, it will be p is equal to 6 delta r square by 2 plus a dash ln of r plus b dash. Okay. So, now you see that at r is equal to 0, this pressure has got some finite value. On the other hand, ln r is an indefinite value quantity at r is equal to 0. So, therefore, a dash has to be equal to 0. Okay. So, therefore, p will be equal to 3 delta r square plus b dash. Okay. So, we have done all that over here. So, finally, this is p is equal to 3 delta r square. So, yeah, so p dash I have written C2 basically same thing. Now, writing in dimensional form. So, it is p is p by p star. So, p is p by p star. So, p star is mu by epsilon square. is equal to 3 into this is delta by h and r square. So, r square is r by a square plus okay, C 2 is fine, C 2 here let us say. So, this P is equal to therefore, will be equal to this is 3 mu into epsilon square. So, epsilon square is h by a whole square and this is delta by h and r square by a square. So, r by a square plus C 2. So, 3 delta r square is r by a and mu by p is mu by epsilon square is p star is mu by epsilon square. So, let me write mu properly, mu by epsilon square. So, here therefore, p is equal to this. Now, at p will be actually equal to 0 at r is equal to a. Okay. So, from there we will get C 2. So, at r is equal to a, p should be equal to 0 and from there we will get here p by p star is mu by epsilon. I have already written it like that and it will be equal to C 2 okay, is equal to minus 3 into delta by h. So, here where I wrote b dash, let me write it C 2 here because otherwise it will create confusion in your mind. So, it is same thing. Okay. So, p is equal to 0. Finally, we have this expression for p and p is equal to p star into. So, p star is mu by h square by r square. So, that r square goes up in the denominator. So, finally, we have this expression and here we can write in further compact form as 3 mu delta by h cube into r square minus a square. So, let me now find out the total load that needs to be applied. So, that is p into 2 pi r into dr 0 to a and so that will be equal to this is 2 pi 3 mu delta by h cube. Okay. So, 3 p is a 2 pi 3 mu delta by h cube 0 to a and r is r cube minus a square into r dr. So, this is equal to 3 mu. So, yeah, so that is 6. So, 6 pi and then mu into delta by h cube. Now, I can integrate it, it is r to the power 4 by 4. So, it is a to the power 4 by 4 minus a square and this is r square by 2. So, it is a square by 2 here. So, here therefore, it is equal to this f will be equal to, now here it is actually minus p, remember that. So, it is minus over here. So, it is minus over here. So, it is a square by 4. So, it is minus a square by 4 minus plus. So, it is a minus plus. So, it is a square by 4. So, plus a square by 4. So, 6 by 4 is 3 by 2 okay. And this is pi, this is mu, it is delta by h cube into a to the power 4. So, that is the total load that needs to be applied. So, mu is Newton per meter square and delta is meter, a is meter to the power 4 and here it is meter to the power cube. So, this so p is f is equal to Newton, that remains correct. And so, this is the expression for f. So, that is the total. So, the load that needs to be applied in order to compressive load by a distance delta. And of course, we can get the write it little bit more different form and that will also be, this is the same thing the way that I have written here. So, now let us estimate that what is the pull of load that will be required to separate this top plate okay, from the surface when there is adhesion between them. So, when there is adhesion between them, the surface energy is minus W A into the area. So, area is pi a square, remember that. So, pi a square is the area of the contact and so it is like that. And then mechanical low energy, so that is actually minus f into delta and this u a will be delta. So, you have to integrate with respect to delta d, so it will be 3 pi mu by 2 h cube into a to the power 4 and it will be delta square by 2, right, 3 pi mu okay, delta square by 2 a to the power 4 2 h cube. So, this is the elastic energy that is stored in the film. So, now you find the total energy U T, that is equal to 3 by 4 h cube, 3 pi 4 h cube here, and then mu and then a to the power 4 3 pi mu a to the power 4 by 4 h cube into delta square, then minus f delta and minus W a into pi into a square. So, we want to find out minimize energy with respect to a. So, let us find out the derivative with respect to a. So, that is equal to 0, and so this is equal to, this is 3 pi mu 4 a cube delta square by 4 h cube minus 2 W a pi into a. So, this is equal to 0. So, from here I can get an expression for delta here. So, the delta is equal to, this is 2 W a pi into a, and this is h cube. So, h cube goes in the denominator, and this is 3 pi mu and a cube. So, a cube here. So, a cube, so I can get it, write it a square and square root. So, 2 W a pi a h cube by 3 pi mu, and this is a cube here and delta square. So, it is like that. So, this is the expression for the critical distance by which this top plate has to be moved upward in order to separate this top plate from the surface when there is a work of adhesion W a, okay, at the interface. So, therefore, this quantity, let me write it little bit clean manner. So, this is 2, this is W a and pi. So, pi gets cancelled. So, pi also gets cancelled. Then I have 3 mu, it is a square here, and this is h cube here. So, now I substitute this expression for delta c into the expression for F. So, that is the critical load. So, that will be 3 pi mu by 2 h cube into a to the power 4 into delta. So, delta is square root of 2 W a, and this is h cube by 3 mu a square. So, here let me take everything inside. So, let us say that f c by pi a square by pi a square. So, pi a square. So, here therefore, this is 3 pi. So, it is 3 9 yeah, this is 9. So, 3. So, it is 3 here, let us say, and this is 2 square. So, it is 2 here, okay. And then mu. So, it is mu here, and then a square is there. So, a square 4. So, it is a square here, and here it is h cube, here it is h cube. So, h cube, it is taken inside. So, 1 h square of h square. So, let us keep it h here. So, h to the power 4. So, h goes over here. So, it is h here, and W a is over here. So, here it comes out to be like this. Okay. I hope that things are all right. So, now let me just check it, since I have some doubt. No, a can be taken here like this. So, a goes over here, forget it. I think now it is correct. So, it is a by h and square root of 3 mu, and let me see W a, I can write it over here. So, it is like that. So, I know this quantity, this is all right. So, f c by pi a square, this is the critical stress that is required. So, this is sigma c here. So, sigma c comes out to be a over h and square root of 3, okay, mu into W a by h. So, that is the critical stress that is required. So, here I have already done all this. So, finally, I have the answer over here, that is expression for the critical stress that is required to separate this top plate from this film. So, this is the summary of those results. So, I have in this my table these two results, I just have it. So, now suppose the film is a compressible film. So, now we have not 0 in the right hand side, but this particular expression, that is the volume strain. So, we will like to solve this problem a little bit differently using this result. So, here u is equal to this result that we can obtain from this dimensional analysis and all that by simplification and the integration all that. I have already done all that. Now, just the difference is that now the film is compressible. So, the right hand side here is not 0. So, here I will like to solve this problem. So, this is r into u is equal to 1 by 2 mu, this is r, this is dp by dr, and this is z square minus zh. So, del of del r, okay, r into u, so that will be equal to 1 by 2 mu into z square minus zh and del by del r, r dp by d, actually dp by dr, these are all dp actually, dp by dr. So, like that, and then 1 by r, so it is 1 by r here, so it is 1 by r here. So, therefore, del w by del z, so del w by del z, so that will be equal to minus of p by k and minus this quantity. So, it is minus 1 by r and 1 by 2 mu. So, let me take 1 by r little bit this side. So, it is 1 by 2 mu, this is 1 by 2 mu here, and then let us say 1 by r, and this is del by del r, r and dp by dr, actually d already. Okay. Now, z square minus zh. So, we can actually integrate it with respect to z. So, if I do that, then w will be equal to minus of p k into z and minus 1 by 2 r mu into 1 by r d by dr, it is r dp by dr, and when we integrate it, it will be z cube by 3 minus z square by h, okay, and there is a constant, that constant writing because that is 0, because w is equal to 0 at z is equal to 0. So, this is the expression for w at any z. So, now here we can write it like this. Let us now find out the w. So, now at z is equal to h, so the integration we have done. So, now at z is equal to h, w is equal to minus delta. So, that is the way I have written. So, minus delta, because delta it is going inside the film, going at negative z direction. So, this is equal to minus of 1 by 2 mu, and this is z cube. So, it is h cube by 3 minus h square by 2. So, it is actually minus h cube by 6. So, it is minus h cube by 6 here, because h cube by 3. So, 2 h cube by 6 minus 3 h cube by, so minus h cube minus minus okay. So, this is right, and this is 1 by r, and this is dp by dr plus this is d square p by dr square. So, I have just written it, open that, yeah. So, here I have written it like this, so it is fine, minus p by k into z. So, yeah, so far so good. So, it is like this. So, now this term will be equal to h cube by 12 mu, okay, into 1 by r into dp by dr plus d square p by dr square and minus this is p k by into z. So, this is okay, and yeah. So, now we can write this whole expression in terms of p. So, if we rearrange it, we can write it like this. So, 1 by r dp by dr plus d square by dp by dr square minus 12 mu by h square into this. So, we can write it something like this. We can write it something like this. So, d square by dr square, okay, and this is let us say p minus this is delta p minus b minus, yeah. So, p minus let us say delta over h, this is p, sorry, p by k is there. So, it is p by k. So, p minus delta by k h, actually delta k delta by h. So, k delta by h, sorry about that, k delta by h, okay. So, plus this is 1 by r and this is d by dr, and let us write it once again, p minus this k delta by h. Remember, k delta by h is constant with respect to r. So, the derivative is equal to 0. I am just trying to write it in a little bit different way, and then this is plus minus, this is plus here. So, I will write it minus here. So, it is minus, it is 12 mu by k h square, okay, and this is equal to p minus this is k delta by h. Let us see if it is consistent or not. So, this is minus, so other side it goes, it is right plus. So, it is plus here, this is k h square, that is fine, and k delta by h, k delta by h. So, delta by h cube, so k gets cancelled, 12 mu by h into delta, this is fine. So, this looks for all right. So, let us consider this as p bar and this as p bar, this as p bar. So, what I have is d square p bar by dr square plus 1 by r, okay, d by dr and p bar minus this is 12 mu by k h square, okay, into p bar is equal to 0. So, I can multiply this by r square all the terms. So, it will be r square, this will be r and this will be my r square, this will be r square. So, see this equation, okay, this appears in also in fluid mechanics and transport phenomena also. Now, here this equation, okay, this is called the modified Bessel equation. In the modified Bessel equation, this minus will be positive actually, but here it comes to be negative. So, this is called modified Bessel equation, and the solution of it is, okay, in terms of modified Bessel function. So, modified Bessel function it will be like this, p bar, okay, so that will be equal to some constant. So, okay, I have just written it in terms of this non-dimensional quantity. So, let us do it that way. So, I have this equation and then I have everything is fine, only thing is that I have written 12 mu by k h square as 1 upon L square, because this has a unit of 1 inverse length square. So, 12 mu by k h square has an unit of 1 upon L square. So, therefore, this is written like that. So, after you non-dimensionalize using this L, capital L, so you get here this quantity eta. So, once you get that, so this is that modified Bessel equation, and it has got this solution in the form of this modified Bessel function. So, modified Bessel function are I0 and K0, this is 0 here, order is 0th order, because here it is p bar minus r to the power 0, that is why p bar, actually this is no, this is not correct. So, p bar minus this this nu square, nu to the power 0, p bar minus nu or something like that. So, here this nu is actually 0. So, therefore, this quantity is I0, okay. This is the modified Bessel function of the first kind and second kind, it is like this. Now, how does this modified Bessel functions look like? Now, they look like something like this, okay, the first kind, okay, over here and the second kind over here. So, second kind says at x is equal to 0, that means here in our case eta is equal to 0, okay, this Bessel function goes to infinity. So, what it means that r this quantity equal to 0, okay, this p goes to infinity, which is not possible. So, therefore, this C2 has to be equal to 0, okay. So, therefore, we have the solution, okay, of p bar in terms of this Bessel function of the first kind, and so this p is equal to p bar is equal to p minus k delta by h. So, therefore, it is k delta by h plus C1 into I0 of this is r into square root of 12 mu by k h square. So, that is the solution of this equation. So, here in the case of this rectangular this cylindrical geometry, you get the pressure, okay, actually in the form of this Bessel function, and then we have to see that, simplify that, of course. How does this simplify, we will see later, but that is the solution we will get. So, that is the difference that is there with respect to this rectangular geometry. Rectangular geometry, remember, we got it in terms of this cos hyperbolic function, and here in this case we get in terms of this Bessel function. So, I will stop here today and we will take up the rest of the things in the next lecture. Thank you.